The idea behind my PCB motor project was to try and design a smaller and a cheaper motor. But to make this work, you cannot power it from a large and a bulky driver. So the second challenge for this project was to try and shrink down the electronics in the smallest area possible, and simplify the circuit to make it as small and cheap as possible. And this is the final result. I managed to fit all the electronics in an area of an 8mm by 14mm by soldering the parts on both sides of the PCB. Both the motor driver and the microcontroller have a 3mm by 3mm QFN package, and most of the other passive components are O201s. So yeah, it was quite challenging to hand solder. The circuit is quite simple. It has a 3-pin connector that has a supply, ground and a control line. For now I'm controlling the motor speed through software, but my plan is to read a 50Hz control signal on this pin to have something similar to an ASC or a servo interface. To avoid having an extra power supply line, I use the same 5 volts to power both the power circuitry and digital circuitry. I fed power to the microcontroller from a simple LC filter, which attenuates any noise present on the 5 volt rail. The tiny triple half bridge driver that I'm using is from ST. It allows a maximum current of 1.3 amps, which is way higher than what I require. This driver was a little more expensive than if I went for designing discrete half-bridge drivers, but it also includes overcurrent, short circuit and thermal protection, which is pretty awesome considering that this is all packaged in a 3mm by 3mm chip. This motor driver is being controlled by a PIC16F microcontroller. In the beginning of this project I was using a higher performance DS-PIC micro, because I was planning to use a different closed-loop speed control strategy. This consisted from measuring the back EMF of the motor and detecting the zero crossing point to determine the next switching point. This is a very cheap way to measure the speed of a motor, so it is very commonly used in brushless motor CSCs. But unfortunately I was not able to use this kind of control algorithm with my PCB motor, at least with this configuration. Let me explain. When ramping up the speed of a normal brushless motor, it starts generating back EMF voltage on the undriven phase. The problem was that the back EMF generated from my PCB motor was too weak, so the zero crossing point could not be determined. I'm still not 100% sure to why this is happening, but my bet is that the coupling between the layers is not that efficient to generate a current on it. So for now I decided to go with plan B and use a Hall sensor to measure the speed of the motor. The sensor is a little more pricier than just using a potential divider to measure the speed of the motor, but its plus side is that it simplifies the way speed is measured and reduces the overall computation power. So I was able to select a cheaper microcontroller which has much less memory and is not as fast as the DS-PIC, but good enough to do the job. So what I did is just place the Hall sensor just underneath the rotor's magnets. On every quarter rotation the rotor makes, it will sense a change in magnetic polarity, so the microcontroller can determine the speed by measuring the time it takes to go from one pole to another. So it's simple as that. Thanks for watching, guys. Wait, so next month I'm going to give a demo of this project at the Hackaday Super Conference, so see you there.